All right, it is just about 10 o'clock, so we will get started here in a minute. Let me just pull up the PowerPoint. All right, there we go. So we're just going to go basically an overview of what chemistry is today. And so our very first slide is just some definitions for us. So what is chemistry? And chemistry is really a subject that tries to understand why matter, why the environment, why like anything we can interact with behaves the way it does by studying the things that make up matter. Those things being atoms and molecules. And you can really go smaller than atoms, right? And we're going to look at protons, neutrons, electrons. And if you want, you can go even smaller than that, gluons, quarks. We're not going to go that far. That's a little too in-depth for general chemistry. But we're going to stop at protons, neutrons, and electrons. And hopefully the idea of chemistry is if we can understand the parts that make up matter, we can understand how matter works and we can manipulate matter in any way that we want, more or less. So atom is the fundamental unit of matter. And when you combine atoms together, you form what are called molecules. And basically anything that you can touch, see, is going to be made up of atoms. There are some exceptions in the form of like light energy is not made out of atoms, but physical things are atoms. And generally, these atoms are going to be in molecules. Not always, but the vast majority of the time, the things that we interact with are actually molecules. And the pictures I have here are just some very basic examples of molecules, right? So here we have H2O, right? Better known as water, where you have two hydrogens bound to a center oxygen. Now, with molecules, you can change properties quite a bit by just gradually changing what atoms are part of that molecule. What I mean by that is this is hydrogen peroxide down here. Now, the only difference between hydrogen peroxide and water is one oxygen atom. However, they have quite different properties. And over here, this is a little more complex of a molecule. This is something that we would study in biochem if you go chemistry that far. This is called heme. This is basically what is responsible for carrying oxygen in your blood and giving it to your cells. But everything that we can study is made up of molecules. Now, this is a science class, and so we need to understand the scientific approach if we want to do science, right? Because science is really making observations, creating a hypothesis based on those observations, performing controlled experiments on those hypotheses, and either confirming those hypotheses or modifying those hypotheses based on our experiment. And so here in the bottom right, I have the general scientific approach. First, you start with an observation, and you can either go to a law or a hypothesis. So what's the difference? Well, a hypothesis is really just your explanation or your idea of what is going on with the observation. compare that to a law is usually never broken, and it's describing things. Currently in the field of science, not many laws are made anymore. Mostly they go from hypothesis to theory. So once you have some hypothesis, you usually want to run experiments on it. So you're going to test your hypothesis through an experiment. Then based on the results of your experiment, you can modify your hypothesis, or if you run enough experiments and your hypothesis seems to be true, then you have what's called a theory. In theory, you continue to do the same thing. You want to test your theory to make sure it is in line with experiments. So again, it's another cycle here. One thing that is different from scientists and non-scientists is the way we use the words hypothesis in theory, right? And you can often see this come up when you talk about controversial theories, like the theory of evolution, for example. And one of the discussion points when you talk about the theory of evolution that you might get from non-scientists is, why would I believe that? It's just a theory, right? And so that's a misuse of the word theory. Theories are backed up by a ton of data. It's backed up by a ton of experimentation. When people usually use the phrase just a theory, a scientist would probably say, well, that's just a hypothesis. A hypothesis is the thing that you have before you start doing experimentations. After you do experiments and you get information, that's when you upgrade a hypothesis to a theory, showing that it's actually been shown in an experimental setting. So that's just something I like to point out, as it's often confusing to non-scientists when they hear the word theory, because in everyday speech, theory doesn't mean something that's backed up well, while in scientific speech, a theory means it's backed up really well by experimentation. And I didn't mention this before, but if you have questions, feel free to pop it in the chat, and you can always send me a private message if you don't want other people to see it as well. All right, so here's our first question of the semester. And since this is the first one, I'm gonna briefly state what the purpose of these are. So during lecture, I will have questions like these. These questions are to test your understanding of the material. You don't get any points for doing them. You don't lose any points for doing them wrong or getting the incorrect answer. They are just there for you to test yourself to see if you understand what I've talked about in the videos and what I've talked about today. And since we are doing this online, I have a Zoom poll. So let me pop that up right here. All right. So periodically through the semester, if I have questions that are easily answered in a Zoom poll, I will pop that up. So hopefully you see that now on your screen. So please, for each of these statements, see if it's describing an observation, a theory, or a law. And with these Zoom polls, they are anonymous, so I can't see how you answer other than percentage of people who gave a specific answer, but no names are put towards answers. I can't see how any individual person answered. So take a minute or two, see if you can figure out what these statements are. Are they an observation? Are they a theory? Are they a law? So I'll give everybody a couple minutes to do that. If you have questions, please let me know. Oh, and one more thing. These questions are a good representation of what you might see on our tests. Like I said on Wednesday, I get my inspiration for making tests from these in-class questions. We'll do about 20, 25 more seconds of this. So please get your answers in if you haven't done so yet. All right. So let's go over these. All matter is made out of tiny indestructible particles called atoms. And I can share the results if you want to see how everybody voted. This is a theory. This is called atomic theory. Believe it or not, everything made out of atoms is not a law, it's a theory. And it's not an observation because you actually physically can't see an atom. We can do experiments to know that atoms are there, but we can't actually see atoms. It's not a law because we don't, it's kind of hard to explain, but the easiest explanation that I can say is that unless you look at everything that's made out of matter and see that it's made out of atoms, you can't really call it a law. So it's a theory. Every time we find matter, we theorize that matter is also going to be made out of atoms. And so far it is. Just to hammer home the point of the word theory, some other popular theories is gravitational theory, right? Gravity is not a law, it's a theory. And the theory that the Earth goes around the sun. That's not a law, that's a theory. So yeah, you can see scientists use theory a lot different than you might on a day-to-day basis. All right, so when iron rusts in a closed container, the mass of the container and its contents do not change. That's an observation, right? You can do that in an experiment. You can see if I put iron in a closed container, leave it there for like 2 years, come back, the weight of the container doesn't change, right? So that's an observation. In a chemical reaction, matter is neither created nor destroyed. Yeah, that is the law of conservation of mass. And that law is just describing this happens in a reaction. Doesn't say why it happens, just says it does. So that is a law. When a match burns, heat is released. Yep, you can put a match, you can light it, put your hand over it, and you can observe that it's hot. So that's an observation. Chlorine is a highly reactive gas. That one is, I would also state as an observation in that you can observe that it happens. If I have chlorine in a container and I put other elements in there, it reacts very violently. So that's an observation. And if elements are listed in order of increasing mass from their atoms, their chemical reactivities follow a repeating pattern. This one I've had people argue with me. So I can see it being a theory that is like, it is a theory, it's periodic theory. People are also can say it's an observation. If you put it there and I observe it happens, sure, you can observe that as well. So I would kind of go either way with that based on how you're describing it. All right. So any questions about the difference between observations, theory, or law? And sometimes it's not exactly clear cut, like when does something become a theory or a law? A lot of that is with kind of like experience, and laws kind of just describe what the result is while saying why the result is that way. All right. And well, if you do have questions and you continue typing, please let me know. Otherwise, we will move on. So in chemistry, these molecules that we study, they have different forms. We're only going to talk about 3 forms: solid, liquid, and gas. There's other forms like plasma, but that's for higher levels of chemistry. But in the videos, I did talk about these. So, and from your day-to-day experience, I want everybody here to take a minute to define what's a solid, what's a liquid, and what's a gas. And when you do this definition, I want you to include things about the volume, the shape, and the movement of atoms. Now, I will give you the answer here in like a minute, but I want you to actually try and come up with your own definitions. Because when learning skills, any skill, it's a lot more valuable for you to try it than for you to wait to listen to the answer. Because if you try it, you're going to get that connection in your brain way faster than just listening to the answer. So see if you can come up with definitions for solid, liquid, and gas. All right, so let's just start with the solid. And there's a fair number of you in here, so let's see if collectively we can get these together. So let's start with volume of a solid. Is the volume of a solid fixed, or does the volume of a solid change? What do people think? It is fixed. Yes, correct. A solid doesn't change volume. It has a volume and it doesn't change. How about the shape? Does the shape of solid change or is it fixed? Yep, Very good. It's fixed. You tried to put a solid brick in a beaker. The brick's not going to change into the shape of a beaker. It's going to smash the beaker. So the shape's fixed. How about movement of atoms? Do atoms inside of a solid move? No, 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 vibrates. Also, the correct answer is vibrations. And everything around you in your room, the computer, the desk, the seat, the carpet, the walls, they are all constantly moving. Granted, that movement is just vibration. And the vibration is so small, you can't like feel it, but it is vibrating. Does anyone know what would we call it if atoms had no movement whatsoever? Does anyone happen to know what state that is? It's very cold. It's lower than freezing, because freezing just means it's a solid. It's way colder. Sub-zero, it is colder than sub-zero, depending on what temperature scale you're talking about, though. Absolute zero, there it is. So absolute zero, which is the coldest you can ever be, is a state when atoms lose all movement and they are completely frozen. And as far as we know, absolute zero is impossible to get to. You can never actually be at absolute zero. You can be awfully close, like 0.000, like 20 more zeros, 1. But so far, we have never got absolute zero. But absolute zero is the temperature where atoms don't have any movements. So yes, solids do have movements. Liquid, I will just fill in the rest now. Liquid, volume, is fixed as well. You cannot compress a liquid. The volume is fixed, but the shape, not fixed. And more correctly, we say the volume, the shape of a liquid will take the shape of its container, as shown here. In the middle there, we have liquid, and it is taking the shape of our container, unlike the solid there on the left. Movement, three-dimensional movement in the liquid. So as long as you're in the liquid, you can move in all 3 directions. And you also spin, you vibrate, you more or less have free motion inside the liquid. Gas, volume, not fixed. So a gas will take the volume of its container. So if you have a balloon and you blow air into that balloon, the air you blow in now has the volume of that gas, where previously it had the volume of your lungs because you blew it from your lungs into the balloon. The shape, not fixed. It takes the shape of whatever it's in. Movement, 3D. It has like no boundaries. It can move 3 dimensions in the whole container, and it can spin, it can vibrate as well. So that's the 3 types of matters we're going to look at: solid, liquid, and gas. Any questions about the material we're going to look at or their properties? So it is, I don't know, I thought it was a little weird that like the seat you're sitting on is vibrating and you can't feel it. But again, we're talking about small particles and tiny vibrations. All right, so we looked at the types of matter we have. Now let's look at how we classify it. scientists love to group things into different categories. If those of you who are biology majors, yeah, you probably know this if you've taken Gen Bio, just looking at all the different classifications you have there. We do the same thing in chemistry. So from matter, we have two different types of matter. We have a pure substance and a mixture. A pure substance is just one element or compound, while a mixture is many elements or compounds. So for a pure substance, we either say, is it already in its simplified atom? That would be an element. So here we are looking, and I know the words are cut off for you, but this is helium. So in this balloon, we have nothing but helium. So this, we're just going to say this substance is an element. On the right, we have water. This is, so this is water. And this is a compound, because we can take water, which is H2O, and break it down further into oxygen plus hydrogen. Helium, we can't break that down further without going into nuclear chemistry, and we're not going to talk about nuclear chemistry. On the right, we have mixtures, and two different types of mixtures, heterogeneous or homogeneous, right? So the picture we have on the left for heterogeneous is wet sand, while on the right, we have tea with sugar. So let's just look at these words. So hetero means different. Homo means same. So anytime you see words that begin with either hetero or homo, that's what those prefixes mean. They mean different or same, right? So heterogeneous mixture is depending where you take a sample from, you're going to get different elements. Or another definition is the elements are not uniformly mixed. In our example of wet sand, you have a water layer and you have a sand layer. Depending where I take my sample from, I'm either going to get more water or more sand, or maybe only water. While tea with sugar, if the sugar is dissolved, right, no matter where I take my sample from, I'm always going to get the same ratio of tea to sugar, because when you dissolve something, it uniformly spreads. So this is a homogeneous mixture in that no matter where I take my sample from, I always get the same components out, the same ratio of components. It's uniformly mixed. So that's the difference between our mixtures there. So let's see if we can look at images of molecules and determine pure substances or mixtures. If we're looking at a pure substance, tell me if it's an element or a compound, if it's a mixture, homogeneous or heterogeneous. In these pictures, you're looking at different atoms, A, B, C, and D, and I have a key down here to know what atoms you're looking at. So I'm going to put the pole back up. If the pole is too big and you can't see the pictures anymore, you can minimize it. And then if you want to, once you have the answers, if you go back to the top of the window and click the poll button, it should pop back up for you. But take a minute or two, see if you can figure out, looking at images, are we looking at substances or are we looking at mixtures? So we'll do about like 20 more seconds. All right. So looks like A and D, we are pretty confident on those as a whole. B and C, maybe not so confident just from looking at pictures. So let's do A and D first. So both A and D are, they are substances. Substance. And A, that's a compound. D, that's an element, right? So the difference between an element and a compound is that a compound is made out of multiple elements. Here we have carbon bound to an oxygen, bound to an oxygen. So this is carbon dioxide. Here we have just hydrogens floating around. These hydrogens aren't connected to anything. So that's just a pure element. Okay, so B and C are our mixtures. And the most confusion that I saw was through B. Well, let me just give you the answers quick, then I'll explain why they are that way. So B would be homogeneous. C is heterogeneous. Let's talk about C, because I think that one's way easier. So here we have two distinct layers, right? We have a layer of water, which is on the bottom. And at the top, what that actually is that's oil, right? 1, 2, 3, 4, 5, 6. That looks like hexane to 2, 4, 1, 2, 3, 4, 5, 6. Yep. So we're looking at what happens when oil and water mix. Well, they separate into two distinct layers. So depending on where you take your sample from, you're going to get a different ratio of oil to water. B, I can see why people might have thought that you're in two separate layers, but this is actually showing mixing happen on a atomic scale, right? Where in reality, these would be moving around. And so these molecules are free to go and interact with the water without having to be in a separate layer. So they would be uniformly mixed. Again, we're looking at a very, very small snapshot of a greater picture. If you're wondering what those molecules are, that is CCOH, better known as ethanol, better known as alcohol. Yep, so B is a picture of drinking alcohol. And when you take a drink, you're going to get a uniform ratio of ethanol to water. So it's a homogeneous mixture. All right, so any questions about our classifications there? Okay. Oh, and I did mention this on Wednesday, but I'll mention it again. All these answers I do post online as well. So if I ever go through a little too fast and delete like something, I do post all these answer keys as well. All right. I think, yeah. So the last thing we're going to talk about today is the difference between a physical property and a chemical property. So we've been talking about atoms and molecules today. And now we're going to talk about the different properties these molecules have. And we put those into two camps. A physical property is a property that happens without changing bonds. right? So when you observe a physical property, no bonds are changing. No chemical bonds are changing. For example, smell. If you smell gasoline, you're not fundamentally changing gasoline itself, or the gasoline is not changing at all. So this is a physical property. The way something tastes, when you taste something on your tongue, that taste is not from breaking down anything, it's just the molecule itself. Color, if I look at something that's blue, I'm not changing the molecule of that blue pigment, so it's blue. Melting point, boiling point, density. None of those have to do with breaking bonds. They're all physical properties. While a chemical property is due to bonds changing. So when you observe a chemical property, bonds are being changed. So if I light gasoline on fire, the gasoline will burn due to bonds being broken. So if something is flammable, that's a chemical property because it involves bonds breaking. An acid, when something is corrosive, bonds are being broken. Toxicity, when something is toxic to us, it's usually because our body breaks it down and then it gets stuck somewhere in an enzyme or something. So that's also an example of a chemical property. Basically, like I said, the rule of thumb is, are bonds being broken with this property? If no, it's a physical property. If yes, it's a chemical property. And so the last question for today is, I have 3 pictures for you. Based on these pictures, I want you to tell me, are we looking at a physical change or a chemical change? That is this a physical property or a chemical property? And one last poll for you. So tell me, do you think the pictures are showing a physical change or a chemical change? And again, these are atoms, and I have the key down at the bottom there. So take a minute or so to do that. All right, seems like we got this concept down pretty well. I'll just go over the answers briefly then. So here in A, we're not breaking any bonds. We're going from a solid to a liquid. So we're melting something. Melting doesn't break any bonds inside the molecule. So this is a physical change. In B, we have oxygen and we have methane. We are combining the oxygen and the methane to make water and carbon dioxide. We are breaking bonds. This is a chemical change. Also, when you burn any carbon compound, you always get water and CO2 out. That's a fun little reaction there. Lastly, we have water. So this is either liquid. I think this picture is supposed to be showing a liquid, and it's going to a gas. So the molecules are becoming more spread out. We don't change the actual bonding of the molecules. So this is a physical property. And that is the end of our first lecture. Not too bad, I hope. Relatively simple, these first few lectures. But with that, I have nothing left for you today, so we can actually get off about 10 minutes early. Just as a reminder, I will be putting up homework here in a little bit on mastering chemistry that goes over the same problems or the same ideas we did today in lecture. That will be due next week. So make sure to do that. As always, make sure you're doing your reading guides and your quizzes for each day. If you have questions, please don't hesitate to reach out by email, and I'll be happy to answer those. Otherwise, I have nothing left for you. So hope you all have a good weekend, and I will see you on Monday. Take care, everybody.